The topic of this presentation is the Pearson correlation coefficient. You now have the tools for examining the association between a categorical and quantitative variable, analysis of variance, and in the case of two categorical variables, the chi-square test of independence. If you have a quantitative explanatory variable and a categorical response variable, for our purposes, I'm encouraging you to categorize the quantitative explanatory variable and use the chi-square test of independence to examine the association. The final inferential tool for examining the association between two variables is the Pearson correlation. The Pearson correlation is used to examine the association between two quantitative variables. You might remember that when we discussed graphing two quantitative variables, we learned to examine this relationship looking at a scatter plot. A discussion of the correlation coefficient and corresponding p-value will now allow us to evaluate whether or not the relationship that we observe in the sample holds for the larger population. The correlation coefficient, usually indicated with a lowercase r, is a numerical measure that assesses the strength of a linear relationship between two quantitative variables. The value of r ranges from -1 to +1. And not surprisingly, negative values of r indicate a negative direction for a linear relationship between the two variables, and positive values of r indicate a positive direction for the linear relationship. Values of r that are close to 0, whether they're negative or positive, indicate a weak linear relationship. And values that are close to -1 or close to +1 indicate a strong linear relationship, either negative or positive. Let's look at an example. A Pennsylvania research firm conducted a study in which 30 drivers of ages 18 to 82 years old were sampled, and for each one the maximum distance in feet at which he or she could read a newly designed sign was determined. The goal of the study was to explore the relationship between a driver's age and the maximum distance at which signs were legible. The explanatory variable is age, and the response variable is distance. Here is a scatter plot for the data, which shows a negative linear relationship between the age of a driver and the maximum distance at which a highway sign was legible. What about the strength of the relationship? It turns out that the correlation between the two variables is r equal to -0.793. Since r is less than 0, it confirms that the direction of the relationship is negative. Since r is relatively close to -1, it suggests that the relationship is moderately strong. In context, the negative correlation confirms that the maximum distance at which a sign is legible generally decreases with age. The correlation only measures the strength of a linear relationship between two variables. It ignores any other type of relationship, no matter how strong it is. For example, consider the relationship between the average fuel usage of driving a fixed distance in a car and the speed at which the car drives. Our data describe a fairly simple curvilinear relationship. The amount of fuel consumed decreases rapidly to a minimum for a car driving 60 kilometers per hour and then increases gradually for speeds exceeding 60 kilometers per hour. The relationship is very strong, as the observations seem to perfectly fit the curve. Although the relationship is strong, the correlation, r, is equal to -0.172, which indicates a weak linear relationship. This makes sense considering that the data fails to adhere closely to a linear form. The correlation is useless for assessing the strength of any type of relationship that is not linear, including relationships that are curvilinear, such as the one in our example. Beware then of interpreting the fact that r is close to 0 as an indicator of a weak relationship rather than a weak linear relationship. This example also illustrates how important it is to always look at the data in the scatter plot, since, as in our example, there might be a strong nonlinear relationship. that R does not indicate. The same can be said for a large correlation coefficient, so it's important to interpret both the scatter plot and the correlation together. As with the other inferential tools that we've discussed, an associated p-value is also calculated for the correlation coefficient, and it is interpreted as significant when it is less than or equal to 0.05.
To demonstrate how to request a correlation coefficient in SPSS, let's go back to the scatter plots that we created for a few of the Gapminder variables. You may remember these scatter plots that I presented to you when talking about visualizing the association between two quantitative variables. The first graph on the left shows the rate of internet use by the rate of the country's population living in urban settings. The second, on the right, shows the rate of internet users by income per person. From looking at the scatter plots, we can guess that the associations are both positive. That is, a higher internet use rate is associated with both higher urban rates and greater income. Now let's find the correlation coefficient using SPSS. As with any analysis in SPSS, we begin by going to Analyze. Simple enough, there is a tab for Correlate. We are performing bivariate correlations. When you select this, it will prompt a new screen. Under Correlation Coefficients, we see that Pearson is already selected. Thus, all we need to do is add the variables we are interested in using. Click OK. A cross table will now appear in the results. In each cell of the cross table, we have the Pearson correlation, the significance, and the number of observations with valid information that are used in the correlation. The first cell looks at urban rate against itself. Logically, it is perfectly correlated, so there is a value of 1, and the p-value is not presented. The n value is all valid observations for this variable, 203. The next cell compares internet use rate against urban rate. Here I see the correlation coefficient is approximately 0.61, with a p-value of 0.00. This tells us that the relationship is statistically significant. This cell also contains the same information, as it is looking at urban rate against internet use rate. Finally, the bottom right cell compares internet use rate against itself. Therefore, the cells that we are most interested in are essentially this cell and this cell, which provide the same information. In this command, I could have added income per person to create a 3x3 table, or I could rerun the command replacing urbanicity with income to create a second 2x2 table. Let me rerun this correlation, but for income. When I rerun the correlation for income, I find that the association between income per person and internet use rate is positive and statistically significant. The coefficient is approximately 0.75, and the p-value is 0.00.
So now we can actually interpret the scatter plots and the coefficients together. The association between internet use rate and income, the second scatter plot, is fairly strong and also positive, as the scatter plot had already shown us. The association between internet use rate and urban rate is also positive, but slightly more modest at 0.61. Both are statistically significant. That is, for both associations, it is highly unlikely that a relationship of this magnitude would be due to chance alone. At this point, I am really happy to tell you that post hoc tests do not come into play in the context of Pearson correlation. Post hoc tests are needed only when your research question includes a categorical explanatory variable with more than 2 levels. Because our explanatory variable in the context of a correlation coefficient is quantitative, there is never a need to perform a post hoc test. So today I'm going to let you go a little early, But before I do, there's just one last thing I want to say about the correlation coefficient. If we square the correlation coefficient, that is, we multiply it by itself, we get a value that is also helpful in understanding the association between two quantitative variables. Little r squared is the fraction of the variability of one variable that can be predicted by the other. For the relationship between urban rate and internet use rate, if we square our correlation coefficient of 0.61, we get 0.37. This could also be interpreted the following way. If we know the urban rate, we can predict 37% of the variability we will see in the rate of internet use. Of course, that also means that 63% of the variability is unaccounted for. If we square the correlation coefficient for income per person and internet use rate, we get a value of 0.56, suggesting that if we know income per person, we can predict 56% of the variability that we will see in the rate of internet use, which is a little bit more impressive. That is, we can predict over half the variability. Again, correlation coefficients are commonly denoted with a lowercase r, and they're squared to determine the amount of variability that can be predicted. You might be wondering how much variability in internet use rates can be predicted if we consider both urban rate and income per person. A multivariate inferential tool called multiple regression can be used to answer this question, but we won't be getting into those details here. For assignment 8, you'll be running and interpreting correlation coefficients. Enjoy.